The problem is about, it began with a human event. Colleague in India proposed to me this problem of the swarm of honeybees hanging from a tree branch in India. Sometimes it gets really hot there. And so the bees, just like these other examples, have a mind of their own, and they create upward channels. This leads to a poor man's model of what happens inside any box that generates heat and hangs in cold air, such as your laptop, or before you were born, the telephone booth. The telephone booth was packed with electrical circuits, and those boxes were generating heat. And if you were into investigation, you found that inside those boxes there were spacings through which the air was invited to rise in chimney flow manner. So here is the model that I propose: a space in a gravitational field, a space of height h and horizontal dimension L. In other words, a two-dimensional model. And in it, the electrical circuits are distributed uniformly through the volume in this simple way. They're printed, if you want, on vertical plates. So the vertical plates generate heat. But before I get to that, there's a spacing between them called the capital D, and a number of such plates, which is obviously L divided by D. And the unknown in this exercise is the spacing, and that unknown is synonymous with the number of plates, because H and L are fixed. So the volume is fixed, but what represents a single degree of freedom is either N or D. And for my formula with this equal sign to be correct, this N must be sensibly greater than 1. Greater than 1, so that what happens near the left and right sides is not a complication that should contradict me, you see. And yes, the challenge is to figure out this particular drawing, which means the value of N or D, such that this heat generating package is the coolest, meaning the one with the best chance of not melting down. And the presentation proceeds from let's call it a constraint, or an idea that is given to us by the electrical engineering arm of this particular design. A group of thinkers would tell us that the electronics, or the circuitry, must not get hotter than a particular temperature called the temperature ceiling. So the temperature ceiling, which is called Tmax in the textbook, is known. What is not known, again, and what depends on the degree of freedom, is the total heat transfer rate generated by the package, or for that matter, the number or volume of electronics installed in this, let's call it computer, or avionics in the cockpit of the airplane. So there is a total heat transfer rate that belongs to the box, and that obviously is is equal to N times the heat transfer rate generated by a single plate. And a single plate gives its Q1 divided by 2 to this rising air, and the other half to the other. You see? So we have, yeah, if you want.
But do these channels have to be straight, or are they just straight for the sake of the problem?
Straight because I'm trying the simplest first.
Right, because like in real PCs, they're like.
Where?
In real computer systems, they're not. Straight,
yeah, but
like,
forget about the real computers. This is pre-computer. This is, yeah. I can tell you the story of this idea. It's really the work of the ignorant, but the one who is unbiased while tackling the idea. So, to your invitation to share, that is why this drawing is so simple. And how do I find this design that guarantees the coolest package? Well, obviously, I have to make a choice between a number of plates that's too small and one that is too big, which means a spacing that's too wide and one that's too skinny. Of course, we'll arrive once again at Roman 1 and Roman 2. So we begin with in other words, this is, if there's one lesson that repeats itself throughout the course, it is a lot easier to predict what happens in the extreme or in two extremes. Those are a lot simpler than in the middle, where the two extremes are at each other's throats. Okay? So we start first with a small d limit. And, here is a blow up of this, not that, a blow up of the channel in the small d limit. Of course, here's the channel is really tall relative to its spacing. Rising through the channel is a stream. This is a narrow chimney, a stream of cold air. I meant to write cold air rising here, and here, and everywhere else. The height is h. Into the channel, the sides are pouring Q1 over 2 and Q1 over 2. In other words, Q1 is the total rate of heat transfer to the stream m dot. And a simple drawing reminds you of a simple drawing from the past. For example, from first course in thermodynamics, this rectangle called the channel is a control volume. This is a system, in thermodynamics, a system, an open system, in the steady state, with a cold stream entering. Exiting is warmer. While being heated along the way with a heat transfer rate Q dot 1. And so the first law of thermodynamics dictates, this is what the law is. This is why everything and everybody obeys the law. Dictates that this Q1 that enters the channel matches the enthalpy rise experienced by m dot 1 through the channel. That's the inlet, cold air, and the outlet, warmer air. This is where your ability to think comes into play. How much warmer is the exiting air? Remember, you're in the business of making your life easy as a problem solver, which means the opposite of splitting hairs. In other words, you said that enthalpy rise is C sub P for air as an ideal gas, T out minus T0. But I'm fishing for the answer to the question, what is T out?
You say it's the same
Same as what?
as T in, or T.
As T0?
Yeah.
Meaning there's no heat transfer to the airstream? But that cannot be.
Why?
Why? Because this is a skinny channel. And it's so skinny that I have the freedom to imagine that I pinch it. I pinch it so that the air in that gap becomes starts mating thermally with the side walls. If the channel is not skinny enough, I pinch it even more. And in that direction of thought, I contradict you, meaning that the exiting air has no choice but to exit at the same temperature as the walls, because the walls are both at T max, which I said somewhere else here. So the walls are at T max, also known as the hot spot. The walls are the hottest entities in this model, and so in this limit of small d,
is T max a predetermined number, or is it?
I just said predetermined because we got it from our neighbors in electrical engineering. Yeah, this is the way to interact with others in a multidisciplinary enterprise. You yes, you learn from them, and then with that information, you try your simplest first. We arrive at T max here, and we'll call this temperature difference. This is actually the temperature difference scale that represents the distribution of temperature in this package. We call it delta T. So with this discovery, we can go up here and continue that in this limit of, never mind. So in the limit of small d, Q1 is m dot 1 and then delta T, sorry, C sub P delta T. The unknown is the heat transfer rate, which will depend on the degree of freedom. And in this limit, we get the urge to declare a victory because we have a formula, except that the m dot 1 is not known. What is the flow rate that seeps upward through the crack? Obviously, it is a flow rate that is completely snuffed out if the spacing d becomes equal to 0. So this m dot 1 is a function of d, the spacing. And what is that? For that, we appeal to another notion we have from more elementary education, I mentioned the word of Poiseuille. The name of Poiseuille. In a vertical crack that's sufficiently skinny, a fluid that flows in fully developed laminar manner. And that means a profile that's this way, parabolic. The length of the channel is h, obviously from bottom to top. And the channel is a slit. Let me give it a third dimension called the W. And there is flow called m dot 1. There's also the command that nothing flows unless it is pushed. So clearly, we know this from the treatment of Poiseuille flow, there's a pressure difference between bottom and top that pushes this chimney flow upward. You see, I take it from the unknown, which is Q1, to the reason why Q1 is an unknown, which is m dot 1. And now I arrive at the real unknown that underpins the previous two, and that is the never before Adrian a question that people did not ask. What is the pressure difference that drives natural convection or free convection? This chimney flow, you know from your course in heat transfer, is known as free convection. And or natural convection. Natural is like saying self, it happens by itself. Free refers to the fact that you do not need a compressor to push this airflow upward. Except that both notions are, sorry, especially the top one, incorrect. I like to restate the first name. By the way, free convection comes from German because fluid dynamics took flight literally because of the airplane in Germany in the first half of the 20th century. The focus was on, minimizing the expenditure of power in order to propel something through a fluid. Well, free convection, I like to restate it as is free convection free. And the answer to the top line is no, because nothing moves unless it is pushed. So what is this delta P in the atmosphere that surrounds the object? Meaning in a constant pressure environment. You see the contradiction? There's a delta P where everything is at atmospheric pressure. Pretty cool. There must be a delta P because there are lots of things moving. The winds, the oceanic currents, the smoke from somebody who's smoking a cigarette. These things, the smoke plume here from the Duke power plant. Sorry, it doesn't make visible smoke anymore except on a very cold day. Yeah, there's movement. And clearly there's a delta P there that people have not questioned. And the answer to that is the following. Here's the direction upward. And here's the pressure distribution in two places. The obvious is the outside over here, and here is cold. So outside, there's a hydrostatic pressure distribution with a particular slope. You know the hydrostatic pressure distribution In this case, if this is y, would be, let me see how I write this, that the pressure versus y, pressure decreases upward, is equal to minus rho of the cold air times G. Okay? So this refers to the column of cold air that embraces the object. You can call it the reference pressure distribution. Inside the channel, things are different. This channel is so skinny that the air in it is essentially as hot as the walls at T max, at a different temperature, meaning a different density. So the density inside, I'll call it rho H from hot, is lower than the density outside, and so the distribution of pressure inside the channel is not as steep. So this one is outside or exterior. This one is interior. Simple sketch, which teaches two things. At the inlet, meaning at the bottom, the pressure outside is greater than in the channel. So it is for that reason that air from the outside rushes into the channel. Admit it, you never thought of this. Why the chimney sucks air from the room? In other words, this thing is an indication that at the bottom there's a pressure difference. It's called inflow. At the top end, the opposite happens. The pressure at the top of the chimney is greater than outside, and the visible effect is called outflow. So there are these two segments. I'll call them delta P at the bottom and delta P at the top. That amount to the delta P, the pressure difference that's responsible for making the air, first of all, squeeze itself into the gap and then get out. So this is the delta P that sparked my interest. Clearly, delta P, according to this formula, is the well, you got two of these expressions. So you got the big rho minus the small rho, which is that of the hot air, and then GH. So the difference in the density from the outside to the inside multiplied by GH is the delta P. Now, what is this? Forget about density. Nobody's going to go around and weigh a volume of air. From thermodynamics, if you remember, the density of an ideal gas decreases with increasing temperature. In our case, we have two temperatures of interest, T0 and T max. And the decrease in this usually a very narrow range of degrees Celsius or Fahrenheit, the decrease is small, but it is definitely monotonic. Let's call it this way. From these two values. In other words, there is a decrease of size delta rho, which is this delta rho, which is obviously proportional to the delta t. Because the slope of the line is just one slope. And it is known in thermodynamics by a coefficient of volumetric thermal expansion. So the formula that we borrow from thermodynamics is that this delta rho is in fact equal to a density which represents both of these densities, meaning order of magnitude density called rho, corresponding to this band of values, and then beta delta t, which is over here. Beta is the coefficient of volumetric thermal expansion, which, by the way, for an ideal gas is equal to, surprisingly, equal to the inverse of the absolute temperature, thermodynamic temperature of the air, T expressed in degrees Kelvin. All right.